Once a model is fine-tuned, the next challenge is serving it quickly, reliably, and cost-effectively. vLLM helps turn that model into a production API by improving batching, KV cache usage, GPU utilization, and runtime control. So far, we've moved from fragile LLM applications towards systems designed for control. The production risks were clear: unpredictable cost, latency spikes, outages, GPU memory failures, and model drift. We then shifted toward in-house inference with open-weight models. Now the focus becomes operational, using vLLM to serve those models efficiently, reliably, and through familiar OpenAI-compatible endpoints. After you choose or fine-tune an LLM, the next major decision is how to serve it. In production, inference is not just a forward pass. Requests arrive with different prompt sizes, generated tokens expand the KV cache, and GPU memory quickly becomes the scarce resource. A naive setup can leave GPUs underused, then still suffer latency spikes or out-of-memory errors during bursts. vLLM matters because it acts as a control layer for LLM inference, improving throughput, concurrency, tail latency, and the cost and reliability of each request. In the production stack, vLLM is the runtime layer that turns chat or completion calls into efficient GPU work. Applications may connect through an OpenAI-compatible endpoint or an API gateway, while vLLM handles the difficult part: scheduling many users at once, generating tokens continuously, and managing memory at high throughput. It can serve open models or fine-tuned variants, while fitting around routing, caching, metrics, tracing, and autoscaling. Think of it as the inference engine, not the entire platform. LLM serving behaves differently from ordinary batch prediction. Requests arrive whenever users show up, and each one may have a different prompt length and stopping point. Generation is also autoregressive. Token 2 cannot be produced until token 1 exists, and each next token depends on the history so far. With fixed batches, some requests wait, and shorter sequences waste compute through padding. The goal is continuous batching. When a request is ready for its next token, the scheduler can feed it to the GPU, keeping throughput high without making users coordinate timing. Continuous batching turns batching into an ongoing scheduling loop. Instead of waiting for a whole group of prompts to finish together, vLLM reevaluates the active batch at every token step. A new request can enter as soon as capacity is available. A finished request leaves immediately, and its slot can be reused. The GPU keeps working on the active set token by token rather than sitting idle between uneven requests. This improves occupancy and throughput without requiring clients to build batches themselves. That higher concurrency is powerful, but it is not free. Continuous batching helps keep the GPU busy by mixing active requests, which usually means more tokens per second and lower cost per token. As volume rises, though, throughput improves only until the GPU saturates. After that point, extra requests mostly wait in the queue, and P95 or P99 latency can spike. The right operating point depends on workload shape. Short prompts, long completions, and bursty traffic behave differently. Tune for sustained throughput, but protect tail latency first. During generation, the model does not recompute attention from scratch for every token. It stores key and value states from earlier tokens in a KV cache, then reuses them when predicting the next token. This makes decoding much faster, but the cache grows as the sequence grows. Its memory cost scales with context length, batch size, hidden dimensions, attention heads, and layers. Long prompts, long outputs, or many users at once can fill GPU memory quickly. If cache blocks are allocated inefficiently, fragmentation can turn available memory into failed allocations and out-of-memory errors. Paged attention treats the KV cache less like one long-reserved buffer and more like virtual memory. Each sequence receives fixed-size blocks as it needs them, and those blocks do not have to sit next to each other in GPU memory. When a request grows, vLLM can attach another block. When a request finishes, its blocks return to the pool immediately. This reduces wasted space from fragmentation, especially when prompts and outputs vary widely in length. That flexibility helps the server keep more requests active with fewer memory-related stalls. In production, paged attention turns a brittle memory problem into a more manageable scheduling problem. Without paging, a set of concurrent long prompts might trigger KV cache out-of-memory errors, even when some GPU memory is technically unused. With paging, cache blocks can be reused and packed more efficiently, so fragmentation drops and concurrency improves on the same GPU. Ohms may fall from several per hour to near zero, while the maximum number of active sequences increases. This still requires operational discipline. Context limits, admission control, and monitoring are needed to protect latency and cost. One practical advantage of vLLM is that it can look like the API your product already uses. If your application sends chat completion or completion requests today, migration may be as simple as changing the base URL, model name, and credentials. Client code and SDK patterns can often stay mostly intact. That lowers rollout risk. Teams can mirror traffic, run canaries, compare responses, and keep an external provider as fallback while confidence builds. The focus shifts from rewriting integrations to validating quality, latency, cost, and operational behavior. A safe migration to vLLM should feel boring to users. Start by keeping the same request and response contract in staging, so the application does not need to change. Then use shadow traffic or replayed logs to compare latency, output quality, token usage, and errors against the hosted API. Once the results look acceptable, canary a small slice of real traffic. Keep the hosted provider as a fallback during this phase. Increase traffic only when your gates hold. P95 latency, error rate, quality score, and cost per request. These runtime settings are the control surface for vLLM. Max model length sets the largest context you allow, but every extra token increases KV cache demand. GPU memory utilization controls how aggressively vLLM reserves memory for weights and cache. Too high can risk out-of-memory errors, while too low leaves capacity unused. Max concurrent sequences determines how many requests can make progress together, affecting both throughput and queuing latency. Tensor parallelism and quantization are the fit and efficiency levers. Use them when the model is too large or when memory bandwidth becomes the bottleneck. Running vLLM in production is an operating pattern, not just launching a server process. Package each deployment with the exact model version, tokenizer, runtime flags, and GPU requirements so replicas are reproducible. Place those replicas behind a gateway or inference router for authentication, rate limits, retries, and traffic shaping. Then monitor the signals that reveal user experience and capacity. Tokens per second, queue time, time to first token, tail latency, GPU memory, KV cache, and errors. Finally, make changes safely with canaries or rolling updates before sending full production traffic. The big takeaway is that vLLM gives us a strong serving foundation. Continuous batching improves GPU utilization. Paged attention makes concurrency more stable. OpenAI-compatible APIs make migration easier. Runtime tuning gives teams real operational control. Next, we build on that foundation with quantization, routing and fallback, autoscaling, and capacity planning to create a resilient, cost-aware inference platform.